So, in this lecture, we are going to see some aspects of parallel architectures and some introduction to parallelization. So, we are essentially now shifting gears, going from the sequential processing to parallel processing, okay. And we are going to see certain aspects of parallel architecture. Tomorrow you have lectures on cache coherence and cache consistency, memory consistency. So, you will see some basic aspects relating to that in this slide, as well as tomorrow you have parallel programming as one of the lectures and parallel programming hands on session. So, some introduction to that is also what you will see in this lectures. Okay, essentially, it is going to be organized as some quick introduction to parallel architectures and followed by parallelization techniques. How do you do parallelization? How do you do shared memory programming? How do you do distributed memory programming or distributed address space programming? That is really what we are going to see. And we could define a parallel machine as a computing system with more than one processor, right. That is really how we would like to define it. And then these processors interact among themselves, interact with each other, and typically they solve a single problem. That is really when we call this as a parallel computer or a parallel processing machine. Okay. Then you will ask the question, which of these things are, according to this definition, parallel process. Let us restrict ourselves to this definition for the time being. There are some other interesting set of machines or architectures which we can look at, but maybe not relevant for this discussion. So, let us look at these things. A multiprocessor system which has a specially designed architectures, either having a shared memory architecture or having a distributed memory architecture, is obviously a parallel processing machine, parallel machine. A multi-core that you can get today is also a parallel processing system. If you have a cluster of workstations or a network of workstations, whatever you want to call that, that is also a parallel processing system, and all of this kind of fall in this definition. So, we are okay with any of these things. We will go more into the details of how a shared memory architecture would look like, how a distributed memory architecture would look like, what are the different types of things in these slides. Okay. So, let us start off with a simple parallel machine which has multiple processing cores, as you could see here, right, and multiple memory modules together giving me a shared memory. Okay. In addition, it could have some level of caching. Okay. The processors are connected to the memory through some interconnection network, and here the assumption is that any processor can actually access any of the memory modules, and the time it takes to access any of these memory modules is kind of uniform, because they all have to go through the interconnection network and access the memory module, right. So, access from this particular processor to this memory, or access from this particular processor to that memory, or access from this processor to that memory, all have the same uniform access time, right. So, this architecture is called centralized shared memory. Okay. It is also called uniform memory architecture, right, uniform memory access architecture, because the access time of processors to memory, any memory, is uniform. The idea here is that any of these processors can access this shared memory which is across. Okay. Now, I will show you another architecture which is what we call as the distributed shared memory architecture. In the case of a distributed shared memory architecture, each processor has some memory which is kind of local to it. It also has a cache, but let us not worry about it. And each processor can also access the memory of another processor, right. In this case, we have a difference in the sense that if this processor wants to access this memory, it does not have to go to the interconnection network, and therefore, its access time is likely to be lower. Whereas, if it has to access the memory of this processor, then it has to go through the interconnect network and it has a larger memory access time. So, essentially this brings non-uniformity into picture, and this architecture is called a distributed shared memory architecture, or what is also called non-uniform memory architecture, NUMA architecture. Okay. So, both of these are shared memory architectures, and in both cases any processor can access the memory available, the shared memory available. All of this local memory put together kind of constitute the shared memory in this particular architecture, whereas all of these memory modules together give you the shared memory architecture. Okay. In both cases the processors, any of these processors can access any of the memory modules. Okay. That's the shared memory. Of course, in order for you to give this shared memory, there is certain hardware abstraction that has to take place. We will talk about that later. Okay. But essentially this processor can access a memory location which is available over there. Okay. How exactly this access goes across the network, gets the data from the other memory and comes back is an issue which we will not directly deal with at this point in time. Okay. And also when you talk about taking the data here and then putting it into your cache, there are certain other issues which come into picture, and again we will talk about this tomorrow. Tomorrow's lectures will deal with that. Okay. At this point in time we want to have this view of how this parallel architecture is going to be, and in this kind of a parallel architecture we have the notion of a shared memory. That is, the processor can access the shared memory and can access the shared memory wherever it is. Okay. Okay. Now, as I mentioned earlier, the centralized shared memory is also called uniform memory access architecture, okay, because any access to any memory location from any processor, right, takes the same uniform access time. Whereas, on this side there is this notion of non-uniformity. If I access the memory which is local to my processor, I am going to have one access time. If I am going to access a memory which is remote to my processor, I am going to have a different access time. Right, that is a non-uniform memory access architectures. Using existing multi-core architecture, some old, some new, we can even give examples of centralized shared memory and distributed shared memory architectures. But okay, so let me just quickly show you one example where we could build, where we could talk about a server motherboard or a server, okay, which has multiple multi-core sockets. So, here you can see two multi-core sockets, okay, each socket having 4 processor cores, okay. And in this case I have a shared L2 cache shared between these two cores, another shared L2 cache shared between those two cores, and so on. And if the data is not available in any of these caches, okay, then it is going to access this through some kind of a shared bus to the memory. Okay. So, this is an architecture of uniform memory access, because whether these processor cores access this memory or these processor cores access the memory, right, if the data is not available in any of its caches, the access time is still uniform. Okay. Now, let us look at a more recent architecture, okay, where I have this notion of what is called, you see this memory controller here, and then there is this is the older processor architecture, that is why I have put QPI, which is the quick path interconnect. Okay. So, here what happens is that these processor cores, if they want to access a memory location which is over here, they will actually go through this memory controller and access it. Whereas, if these processing cores, any of these processing cores wants to access a memory location which is over there, then they will have to go through the quick path interconnect on both sides, go through the memory controller and get the data back. So, this is going to cause you a non-uniform memory access time. Okay. You can build larger architectures of this kind, okay. But both of them, both uniform memory access and non-uniform memory access architectures that we have talked so far are shared memory architecture. There is a notion of memory being shared across all of these processors. It is only their access time is either uniform or non-uniform. That is really the difference. Okay. Let us move on. Let us talk about another kind of a parallel architecture, which is distributed memory architecture. And here the word shared is missing. Please note that there is no notion of a shared memory. Here what happens is that each processor, sorry, went too fast. Okay. So, here what happens is that each processor has its own local memory, but it cannot access the memory across the network to the other processor. Okay. So, that is the assumption. Here there is no notion of a shared memory. Each processor has its own individual memory, which you can see. They are connected by means of a network, but they have no capability of addressing the memory which is in a remote node. In the previous case, when we talked about the distributed shared memory architecture, right, there was a capability of being able to address the memory which is in a remote location, and therefore, all these memory are considered as shared memory. Here that capability is not there, okay, and therefore, these processors cannot access the memory of any of these other processors. However, they can interact among themselves by sending messages across this network, and these messages are typically send receive messages, sending certain amount of data, receiving the data, and so on and so forth. Okay. So, these the processes which are running on these processors essentially interact among themselves by means of these send receive messages. They cannot access any of the memory locations which are in the other nodes. Okay. So, this architecture is what we are going to call as message passing architecture or simply distributed memory architecture. There is no notion of a shared memory in this. Okay. So, clearly we have two sets of architectures, the shared memory architecture and the distributed memory architecture. In the case of the distributed memory architecture, there is no notion of a shared memory. Within the shared memory architectures, we have two types, uniform memory access architectures and non-uniform memory access architectures. From an architecture perspective, you will see a lot more discussion in this workshop on shared memory architectures. Okay. Whereas, in this lecture, I am going to talk about how to program these kinds of parallel machines for a single task. But if you have a shared memory machine, if you have a distributed memory machine, how do you write programming? How do you write a parallel program which has the abstraction of shared memory? How do you write parallel program which have this abstraction or notion of messages? That is essentially what we are going to see in the rest of the lecture. Any questions so far? It's not just a question of synchronous and asynchronous, it's that's one example I showed, but in general when you talk about a non-uniform memory access architecture, the underlying assumption is that some memory is going to be local and therefore its access time is going to be less, whereas some memory is going to be remote whose access time is going to be higher. No, do not confuse message passing with non-uniform memory access. Non-uniform memory access still has the notion of a shared memory, whereas in message passing there is no notion of shared memory. Okay. So, as I mentioned earlier, this processor can only access memory locations here. It cannot directly access or address memory locations here. The only way it can get the contents of this memory location is by sending a message to this processor. This processor doing certain is by sending is actually by doing a receive, okay, from this processor, and this processor cooperating and sending a message or sending the data to that processor. That is really what. Sorry? It cannot write, it cannot read, both. It cannot address the memory in a remote location, right. So, what was making it happen in the case of a shared memory architecture is that the address space was kind of distributed across all of those nodes, and therefore, you know that when I give this address, it is in this remote location, I can go and access, and you have the abstraction, hardware abstraction which is available to go and access that particular location. That hardware abstraction is not here. Okay. But that is one very big advantage of this machine or this architecture, because now you can actually think of each of these things as some kind of processing nodes, and these processing nodes are nothing but your desktops or servers. Okay. And when these desktops or servers are connected with each other by means of a network, interconnection network, they provide you a parallel computing platform, a distributed memory parallel computing platform. Okay. So, this is where cluster of workstations or network of workstations, right, now becoming a parallel computer. Okay. We will briefly talk about what these interconnection networks are, what the topologies are in the slide after this. Okay, why did it skip the previous slide? Sorry. Okay. So, here is another example of how I build a parallel computer. Okay. Here is actually the case of what I call a somewhat hybrid, because each node here has some kind of a shared memory architecture. Okay. And I have multiple such nodes connected by means of a network switch, right. So, technically speaking, what happens here is that the processors here, okay, the cores that you see here, can access the memory which is over there, and this memory could be a shared memory across all of these processing cores. However, the processing cores here cannot access the memory which is over there, that is in a remote node. Okay. So, this kind of has both shared memory and distributed memory architecture together. If you look at from a node perspective, right, the nodes among themselves are having distributed memory architecture connected by means of a network switch, whereas within a node you have some kind of a shared memory architecture. Okay. Today you can think of this as your server, okay, having multiple socket multi-core processors, and they are connected by means of some interconnect network. This could be simply a gigabit network, or this could be an InfiniBand kind of a network, or this could be some other network topology, okay, network connections and network topology, and many of these things are connected together. Okay. Now, just to give a very brief idea about what these interconnect networks are. Interconnect networks are again divided into indirect networks and direct networks. In the case of indirect networks, nodes are connected to the interconnection medium, but not directly to another nodes. In the case of direct networks, nodes are connected with each other directly. Okay. I will give you examples of this. So, for example, if I have a shared bus, or if I have a crossbar network, or if I have a multi-stage interconnect network, and I connect nodes and memory through this interconnect media, okay, then that is the case of indirect interconnects. Okay. Whereas, if I connect the nodes or processors and memory directly, okay, using some kind of a network topology like any one of these topologies, I will show you examples of each one of them in the next slide, that becomes like a direct network. Okay. So, here is so again in the case of a direct network, you need to have some kind of a routing technique and how to route the messages and things like that. Okay. So, again here are examples of indirect interconnection. So, you could see that here I have a set of nodes, processing nodes, and a memory module. Okay. They are connected by means of a shared bus. Okay. This here the shared bus is a kind of a interconnect network, it is a kind of a indirect interconnect network. Okay. That provides, that is the medium through which the processing nodes and memory are connected. Okay. I can actually have multiple such shared buses and connect them. Okay. Or I can have some kind of a crossbar switch which will connect the processing cores to a set of memory modules. Okay. This is a crossbar switch. I could have some kind of a multi-stage interconnection network, where this multi-stage interconnect network essentially has a sequence of switches. Each one of them in this particular example is a 2x2 crossbar switch, and they are connected in some particular pattern, so that every core here is possibly connected to every memory module over there. Okay. And it takes 3 hops here for, let us say, for this message to go like this to that particular memory module, right. If this particular memory module wants to access the core, this particular core wants to access the memory module, then you can see the path that is going there and going to that. Okay. It will take 3 hops to go there and get it. It depends on the number of cores, number of memory modules, and some log of that. Okay. That is really what it is. So, question? Okay. Now, I will give you examples of direct networks. Okay. So, So, here I will mostly take the case of processing nodes being connected to each other. So, you could see a linear connection where the nodes are connected in this way. You could, when they are connected in a cycle, it is called a ring. Okay. When they are connected in this way, it is called a star interconnect. So, here there is a single node which gets connected to every other node, right, and of course, this single node will become a critical node, right, because this is the one which connects everybody. If this node fails, then the entire interconnect goes for a toss. Okay. You could talk about what are called 2D meshes, okay, which is basically n squared processing cores connected by means of north, east, south, west links. Okay. So, each node is connected to 4 neighbors, right, and a message from this node, if it wants to go here, it can potentially go like this, or it can potentially go like that, or it can also go something like this using the routing method. Okay. So, again when you talk about interconnect networks, you talk about how the messages can be routed, what are the routing methods and so on and so forth. This is same as a 2D mesh, but the end nodes are connected with each other. So, it is called a 2D torus. So, you can see that this instead of being linear, this is being a ring. This instead of being linear, it is a ring. So, you could see that everything is connected to everything in a ring fashion. So, this is a torus network. There is also something called a hypercube network. Okay. So, we have a hypercube of n is equal to 2, n is equal to 3, n is equal to 4 and so on. Okay, that essentially will have 2 power n nodes, and each node will be connected to n other nodes. Okay, that's really what's happening there. Okay, these are different types of interconnect network. Perhaps we may not go into any more details of this interconnection network, but just for you to have some idea of what these interconnect networks are. Let us now go back to the programming abstractions and how these programming abstractions get mapped to these different architectures. Okay. Again, remember, we have this notion of shared memory, we have this notion of distributed memory or message passing architectures. Now, from the architecture perspective, that is what we said, shared memory architectures, either centralized shared memory or distributed shared memory. Distributed memory architectures, also known as message passing architectures. But from a programming model perspective, right, when a programmer writes a program to run on these machines, he could either write a shared memory program or he could write a distributed memory program. Okay. Again, there are two possibilities. So, we can say that the programmer has a programming model in which he assumes a shared address space, right. By that, what he means is that there are many processes, but all of these processes kind of communicate or kind of interact with each other through a common single shared address space. Okay. That means that this process may compute something, put it in some memory location. Another process may actually access this memory location and know what has been computed, and then do further computations on that, right. So, that is a shared memory programming. Okay. So, essentially what happens is that they all share a single shared address space, and through that they could actually interact with each other. Any process can read or write any of these shared address space locations, and that is the interaction. The programmer carefully plans or coordinates who writes and then who reads, or when the reader should read and ensure that the writing has already completed. Okay. Those things have to be taken care of by the programmer. Okay. So, one could write such kind of a shared address space program using a programming model or programming language called OpenMP, right. When you talk about distributed memory machines or message passing machines, there the abstraction is more of message passing interfaces. Okay. So, here the programmer writes programs in which there are multiple processes, and each process may not be able to access the memory of another process, however, can send or receive a message from those processes. So, this will typically include sending messages, receiving messages, and doing something more than that in the case of message passing machines. Ideally, the shared memory programs are good for mapping into shared memory architectures, and the message processing program is good for running in the distributed memory machines. However, it is easily possible to run this message passing programs also on the shared memory machine. It is easily possible. However, if you want to run these shared address space programs on the distributed memory machines, you need to have some kind of a software abstraction that is required. Okay. So, let us in general talk about these programming models as shared address space programming models and message passing programming models, with the assumptions that the shared address space programs are typically going to be run in shared memory architectures, and the distributed memory programs or message passing programs are going to be run in the distributed memory architectures, although it is possible to run each one of these in the other architectures also, right, with or without, I mean in one case with the software abstraction, in the other case you do not need it. Okay. That is really where we are. Any questions so far? Okay, what do we mean by software abstraction? Okay, so what do you need here? If you want to run a shared address space program on a distributed memory machine, what is the capability that you need? So, it is a shared address space program. As I mentioned earlier, you should be able to access the shared memory. So, you should be able to access the memory location of another process. Do you have that in the case of a distributed memory machine? You do not have that. The hardware does not provide that abstraction. Because the hardware does not provide that abstraction, somebody else has to provide it. That is the software abstraction that we are talking about. Well, somebody has to program. It is not the programmer, but somebody has to provide that software abstraction, and if that software abstraction is available, then one can run shared memory programs on that distributed memory machine. And that software abstraction essentially ensures that you are able to read and write memory locations in a different process, right. They are able to share the shared address space. Any other question? Okay. So far so good. Let us just okay, again I think this is just a recap of what we have discussed so far. The shared memory programs essentially have a shared global address space, okay, which all the processes can share, whereas in the case of a message passing program, memory is private to each node and communication or interaction is only by means of messages. Whereas in the case of a shared memory program, the interaction is through the shared locations. That is really what it is. Okay. Before we go into shared memory programming and distributed memory programming, or in general parallel programming and the parallelization techniques, let us have a few definitions and understand them well. Okay. So, we are going to talk about Speedup. So, when I am running a program on a shared memory machine, or when I am running a program on a parallel machine, ideally speaking I want to get some performance right out of that. How do I define this performance? One way of saying is that what is the speed up that you get, right, and how do we define speed up? If I run the program on a single processor, how much time does it take, as opposed to if I run the program on, let us say, a machine with 8 processors or 16 processors, whatever it is, right. That is one thing that I can call as speed up. Okay. Ideally speaking, if I am running a program on 18 processors or n processors, I should get a speed up of n at least, I mean not at least, I will expect to get a speed up of n in the ideal case. It may not be n, it may be less than n, okay, but ideally speaking I would like to get a speed up of n, right. So, that is how speed up is being defined. Efficiency, okay, which is basically speed up divided by n, and if I get an ideal speed up, my efficiency is 1. Okay. If I get speed up which is lower than that, my efficiency is less than 1. Okay. We will also talk about Amdahls Law, right. You would have come across Amdahls Law when we talked about processor architecture also. Have you come across? No. Okay. So, what is Amdahls Law? Okay. So, when I am running a program, let us say in a parallel processing machine, theoretically what is the maximum speed up I can get, correct? You would say of course n, right, in n processors it is n, but it does not only depend on the machine and the number of processors, it also depends on the program you are running. Okay, if your program is completely sequential and if you run it on n processors, would you get a speed up of n? No. Let us say if 50% of your program, right, is sequential and the remaining parts are parallel, then what is the speed up that you will get? Huh? Sorry, somebody said 2x, maximum of 2x. How do you know it is 2x? Okay. So, when the number of processors goes very large, right, I can reduce at most the other half of the time close to 0, but the sequential part still remains. That is exactly what is Amdahls law. Amdahls law say that the speed up that you can get is limited by the sequential part, the part which cannot be parallelized, which cannot get the performance benefits of parallelizing, right. So, if 1/4 of your program is sequential, then it does not matter whether you put 10 processors, 10 million processors or 10 trillion processors, you can't get a speed up more than 4, right. So, that is really what Amdahls law says. Okay. And we have to keep in mind, because when you write a program, you have to essentially, when you parallelize a program, you essentially have to make sure that the sequential part of it is reduced as much as possible. Because if 10% of your program is sequential, then you are not going to get a speed up greater than 10, right. That is really what is Amdahls law all about. Okay. Here is an example of Amdahls law. Okay. Let us say that I do some computation on a matrix, n by n matrix, okay, and then I do a reduction that basically add up all of these elements, right. In the sequential case, I will have 2n squared execution time, right. If I do a naive parallelism of this, where I do the first phase, that is the first phase of the computation, okay, using p processors, where I divide this n squared computation across these p processors, assuming that that part is parallel, then I can complete that in n squared by p time. But I might end up doing the reduction in, if I do it naively, I can end up doing the reduction in n squared time, and here, as you know, right, I have only reduced one part of the problem, that is, this first part is parallel, the second part is still sequential, which is 50% of the time. So, I can't get a speed up greater than 2, right. But I can do something smart. I do not have to do this reduction, that is summing up of all the elements sequentially. I can actually do summing up of the elements n squared by p elements in one processor, n squared by p element in another processor. Like that I can do it in p processors, and then those individual sums I can do it sequentially, right. So, that is the other that is the other version. So, you first do the initial computation of n squared by p elements in p processors, okay, that takes exactly n squared by p time units, and then you do local reduction, which is for all the n squared by p elements which are in that processor, you do some reduction, and then eventually you do the reduction of all the local reduced values into one processor, maybe processor 0 or whatever it is, and that takes p amount of time. So, here what you have done is you are now able to get a speed up which is close to p. Otherwise, with this version you would not be able to get a speed up which is greater than 2, right. That is really what Amdahls law says, fairly intuitive, right. So, whenever you are parallelizing the program, make sure that you reduce as much as possible the sequential part. That is the point that is being said here. Okay. We are going to use the word task when we are talking about parallel program, which is basically any arbitrary piece of work in parallel computation. Okay. So, some piece of work, some chunk of work that we want to do, right. It may be parallel with other tasks, sometimes this has to be done sequentially, meaning there has to be some synchronization, then this task has to be executed and then the subsequent tasks have to execute, and so on and so forth. Okay. The task can be coarse grain or fine grain. When we say coarse grain, it is a large chunk of work. When we say fine grain, it is a small chunk, very small chunk of work. Okay. If you have a coarse grained task, then you will have fewer tasks and the amount of parallelism that you can exploit may not be high. But the level of synchronization that you do with a coarse grained task is also lower. Whereas with fine grained tasks you may be able to exploit lot more parallelism, but you will also incur more synchronization overhead. So, there is a trade off between these two things. Okay. We use the word process, which is basically what is being executed in a processor. We will actually use the word process and thread somewhat interchangeably, okay, although these have different meanings. Okay. You could have multiple threads in a process, but we are not going and they could all share the same process address space, whereas different processes will have, each process will have its own address space. But barring that difference, we will kind of use the word process and threads somewhat interchangeably, because when you do multi-processor programming, there are multiple processes which are executing. You can also think in terms of multi-threading, particularly in the case of a shared memory multi-process program, the process and threads, okay, kind of have a similar notion. That's the reason why we use them interchangeably. Okay. Processor is the core or processor where things are getting executed. Okay. Now, let us just look at what are the steps involved in parallelizing a program. Okay. So, essentially one needs to identify the kind of work that has to be done and that can be done in parallel. So, first decompose the problem into as many parallel entities as possible, but you do not want to go and then do too much of decomposition, because when you do that you will have fine grained parallelism and too much of synchronization overhead. So, you may want to group them in some way, okay, so that you have tasks which are large enough, but at the same time you are able to exploit enough amount of parallelism. That is really what you want to do there. Okay. So, that is the second step which is involved in parallelization. The third step which is involved in parallelization is, once you have these different tasks, how do they interact and what do they do? How do they make sure they collaborate with each other to compute what you want to compute? That part is called the synchronization or orchestration. Okay. So, we will talk about each one of them, but first we will talk about decomposition. Decomposition itself can be done in two different ways. You can either do a task level decomposition or a data level decomposition, right. When you do a task level decomposition, you identify these are the tasks, and ideally these tasks are different tasks, okay, and they interact in this way. This task can be done in parallel with this task, but this task has to be completed or can be started only after these two tasks have completed. So, like that you can actually create what is called a task graph, and that task graph can specify the computation that you want to perform, and that task graph itself can tell you how to do the synchronization across these different tasks. That is one way of doing. Another way of doing decomposition is what is called domain decomposition or data decomposition. In this, what you do is that all the tasks typically perform more or less the same work, but they perform it on a subset of the data. So, that is why here what happens is that the data is decomposed across, the data is decomposed into different parts, and the computation which is being performed on this subset of data is what becomes as different tasks. Okay. I will actually give you examples of this one, and many of the parallel programs that we are going to do essentially is going to follow this domain decomposition approach. The earlier example I gave, where we have an n squared matrix, okay, where we are doing certain computation on each element of the matrix, right. I can actually decompose this into n squared tasks, because each one of them is an element. So, if I do a domain decomposition, I can actually perform computations on each one of those elements, right, and that is domain decomposition, and basically each task is performing computation on a single element. Okay. This is also sometimes called owner computes, because you have domain decomposed and then the owner of that domain computes whatever that is required there. Okay. So, here is the example that we want to work with in this. So, here I have a doubly nested loop, okay, right, and I have a matrix where I want to, let us say, add each element of the matrix with a vector. Okay, Aij is equal to Aij plus Vj, right. Okay. right. I just wanted to save. So, what I can do here is that I can now take this entire matrix and I can divide this into subdomains. For example, these 2 rows are one subdomain, right. These 2 rows are another subdomain, and so on and so forth. I can divide this into 5 subdomains and I can create 5 tasks in this particular example. Each one of those tasks working on the subdomain of data that they have been allocated to, and they can perform this computation on that particular subdomain. That is really what I mean by saying domain decomposition, right. Okay. Now, again go back to this various steps involved in creating this. We already discussed this decomposition of the problem into individual computations exposing all the parallelism, that is the decomposition step. Then of course, you want to group some of these decomposed entities into what we call as tasks, that is essentially what is called assignment. I will give you an example of this. Then of course, between these tasks whatever orchestration that is required, which is basically how do you coordinate the data access, how do you coordinate the communication between them, if it is a shared memory program, how do you do the synchronization, etc. That part is essentially what is there in the orchestration. The last part is essentially where do each one of these tasks get assigned to and execute. Okay. That problem is what is called mapping, where you say that this particular process executes on that processor, this particular process executes on that processor. That is essentially a mapping decision. Oftentimes, we may not have a fine control on how to do this mapping. The underlying parallel operating environment would do that for us. So, we may not really see a lot of, we may not really have a lot of discussion on this point. But as a parallel programmer, you still have to do the first 3. And you will leave this mapping of processes to processors to a large extent to the underlying operating environment. Okay? That is really what you do. Okay? Again, these 4 steps in terms of what you do, you take the sequential task, you decompose them in terms of n parallel tasks, okay? But these may be at a too fine grained level. So, what you might do is that you might group these so called subtasks into tasks. So, those are the 4 parallel tasks that you have in terms of domain decomposition. Those are the 4 domains that you are talking about, and between these domains what is the kind of interaction that you would have. So, you want to minimize this level of interaction. So, you form your groups in such a way that this interaction is minimized as much as possible, because whenever you have an interaction, whenever you have this collaboration or message passing or synchronization between them, that incurs a overhead. So, you want to reduce this as much as possible. Of course, where do you place each one of these tasks in terms of their processors, which is the mapping part? We will typically leave this to the underlying parallel operating environment to take care of that. Okay. So, we will not talk more about that. Okay. So, the decomposition step is essentially identifying the different tasks and what tasks can be done in parallel. Okay. And here the goal is to expose as much parallelism as is available. Okay. Later on we will regroup them and then say that this will become tasks. Okay. That's really what is the work of assignment. We group these subtasks together to form tasks, and here the idea is to balance the workload across these different tasks, and also to make sure, right, in some sense you reduce the communication or interactions between them. That's really what you want to have. Okay. Let me just skip some of these things because this is prepared for a different context. The goal of orchestration is essentially to make sure that the interaction between these processes take place as is required in the parallel program, right. If I want to compute this, I have to send a message from here to there, and that particular process has to receive that message. Or if I want to compute this, I have to do synchronization. I have to make sure that the producer has produced the data before the consumer can read the data. So, I want to put all of those things into place there. Okay. So, that is really what I try to do in orchestration, and when I do the orchestration, I also make sure that the overheads are overall reduced. Okay. Again, this choice depends on the programming model, the communication abstraction that you use, and the efficiency. We will not really bother about these things, but we will see an example of how to do these things. As I mentioned earlier, mapping right, is essentially where do you map these tasks. There are two aspects to it, which process runs on which particular processor, and whether you allow multiple processes to also run on the same processor or processor core. Again, these decisions will be taken by the underlying operating environment. So, you may not have much of a control in a parallel processing machine. You talk about what is called space sharing, where the machine is divided in terms of processors and nodes, and one application can run only on one subset and different applications can together run on the entire machine. That is essentially what is called space sharing. You could also specifically pin certain processes to a processor or a node, but ideally speaking this should be left to the underlying operating environment. Okay. So, many of these things, as I mentioned earlier, is going to be handled by the underlying operating environment and we will not worry about it. Okay, I will skip this slide. Okay. Now, let us look at a very simple program. Okay. Here is a program we have a two-dimensional matrix and I am going to do some kind of a stencil computation, right. I will show you the computation in the next slide, and then when I do this stencil computation I am going to find out the difference between the previous iteration and the current iteration, and I will kind of do some kind of a convergence based on that. So, here is the code, right. You can look at it. Essentially I have for each element, okay, I basically do an averaging operation of its neighbors and itself. Okay, that is really what is happening. Each aij, okay, for aij I take aij, ai minus 1j, ai plus 1j, which is basically the elements which are above and below that particular row. Similarly, aij minus 1 and aij plus 1, which are the elements to the left and right. So, I take all of these values, I take the average, I take sum of all of these things, I take the average and I store it in a different array bij, and now find out what is the difference between bij and aij, old value, okay, and I take the absolute value of this, right, and after I do this I copy bij back into aij and I see if the sum of these absolute differences, okay, is less than certain threshold. If it is not less than certain threshold, I iterate over. Okay. So, essentially I do some kind of an averaging operation. This is typically done in many image processing applications, it is also done in various other numerical computations. Okay. Supposing let us say we want to parallelize this program. This is the example, running example that we are going to use in terms of looking at how to parallelize this. Okay. That is really what you are going to see. Any questions on this program itself? Let us not worry about the so called boundary elements, because there are computations, actually nothing is computed there, it is only for the non-boundary elements the computation takes place. Okay. So, let us look at this example and then see how you can decompose this into tasks, how you can group them, how you can decompose them into subtasks, how you can group them into tasks, and how you can do the coordination between them. And in case of shared memory program, what kind of primitives you use, in case of distributed memory programs, what kind of primitives you use. That is really what we want to see. Okay. All right. So, any idea how you can decompose this? Sorry? You take the grid into 4, but why 4? Huh? Some number. Okay. The idea of the decomposition step is to expose as much subtasks as possible. So, one possibility is to say that each one of these grid points is a task by itself, is a subtask by itself, right. That is the level in which you want to decompose it. Okay. Now, what about this iteration? Can I do this iteration in parallel? Can I do computation of bij for different I and j, right. So, if I look at it from a parallelism perspective, right, each one of these grid points can be computed in parallel, because computation of this point, right, does not depend on the computation of this point or on the computation of that point, right. I am going to take the old values or the aij values and I am going to compute bij values. I can do all of these things in parallel, right. So, in the decomposition step, you basically say that you have n squared parallel subtasks, so to say, right. Each element is a subtask by itself. There is a dependency, but how is the dependency manifesting? You are basically taking A values, okay, and then writing it into B value. Okay. So, the circle that I have shown actually represents both A and B. The dependencies are coming from A and they are going into B, correct. In this particular example, where I am writing into array Bij, all of these things can be done in parallel, correct. There is no problem here. Whereas, if I have put Aij here, what you say is correct. Okay. I am going to come to that in the next slide. I wanted to start off in a place where everything is parallel. That is the convergence criteria. Okay. The convergence criteria is the sum of these absolute differences across all of these elements is less than certain threshold. That is the convergence criteria. Okay. So, as long as this is in a different array, all of these operations are parallel and they can be done in parallel. Okay. All right. What about this difference operation? Can that be done in parallel? This is where I am actually computing the difference and accumulating it. So, again I am doing n additions, correct, n additions here. Can I do these n additions in parallel or n squared additions in parallel? Wait for first of all this computation to be over, that is one thing, but even if that computation is over, can I do this? Huh? Okay, what is the issue involved in that? What do you mean by VR? Can you elaborate on that? You said we are reading and writing into the same location, but can you? Huh? Correct. So, who is that we? I wanted to know. Huh? Correct. So, each one of these threads or tasks that we are talking about, right, are going to do this read and write on the same location. That read and write by itself is not a problem, right. Okay. So, here is a situation where, okay, I am going to, so this is typically what you will see in any shared memory program, that when you try to read a value, increment it by 1 and write it back. This is the typical example which is given. You would have done it in your operating systems course, correct. So, whenever you try to do that, after you do the read, which is basically a load, another process might come and read the same value, okay, and you both will read the same value, and if you try to increment, only one of those increments would have happened. That kind of a situation is going to happen here. So, one has to be careful, we have not taken that into account, okay, but for that this particular part of the task can be parallel. Okay. To compute disk, some coordination would be required. One way to say is that, okay, only we can put this diff in what is called a mutually exclusive region, a critical section, right. Can you put this in a critical section? You can put it in a critical section, and when you put it in a critical section, only one process or one thread can execute it at a point in time, and as long as you do that, you are okay, because the computation would actually compute the accumulated value, the reduction will actually happen. But if you put it in a critical section, then what is going to happen? All of them will execute serially. Okay. So, that is really the issue that we are going to talk about and how to solve that. Okay. But that problem of being of multiple processes reading a value and trying to write the coordination between them is a problem that we are going to discuss, and certain solutions for that we are going to discuss in tomorrow's lecture. Okay. All right. So, here I can actually take each grid point as a subtask and I can do the things, but this diff computations would require some coordination. and because of this coordination what would happen is that I would actually incur too much cost, because n squared processes have to coordinate, that might be too much cost. So, I might decide to kind of group some of these subtasks together and reduce this coordination in some sense. So, go from a fine grain to somewhat coarser grain tasks. Okay. And when I want to group these things, I can either assign, go from each grid point to each row of grid points or each column of grid points, or I can talk even about a block of rows or a block of columns, and then I can say that those are the tasks. So, I may go back to what Anurag was suggesting, right, divide this into 4, divide this into 8, or divide this into p, where p is the number of processes. So, I will essentially say that n divided by p rows together will be one task, n divided p rows, another n divided by p rows will be another task, and so on and so forth. So, pictorially what will happen, am I going somewhere else? So, okay. One slide is missing, or okay, let me not worry about it. So, I would have shown the assignment problem here, but before we go into that, or before we talk about that, let us look at another problem, okay, which basically where am I putting is this? Okay. All right. So, let us look at an in place update of the same problem. Okay. Here is where the problem that you have talked about comes into picture. I am saying A I j is basically sum of all of these elements divided by 5. Okay. And when I try to do this, what really happens is that if I want to compute this element, I must have computed this element and this element before, right, and only then I can compute this element. Whereas, for these two elements, based on the sequential program, they are old values of A I j, whereas these two, if I am doing the iteration in this order, these two are new values, these two are old values, this is also a old value, correct. So, essentially what happens is that there is a dependency which is flowing, okay, from left to right and from top to bottom. So, in this particular example, right, if I divide each grid point as a separate subtask, I still may not have all of them executing in parallel, right. So, what happens is that there is a dependency which is running across like this. Okay. I can do the computation of this grid point only after I have finished the computation of this grid point and that grid point, and I can do the computation of this grid point only after I have computed these two. I can do this only after I have computed these two. So, if you look at it, right, in some sense there is a lot of synchronization that I have to do, right, before I can ensure that this task can be executed. If I have put each one of these grid points as parallel tasks, right, then in order for me to say that this particular parallel task can execute, I have to ensure that this parallel task has completed, that parallel task has completed, and then only this task can execute. So, for every grid point I need to do synchronization with two other grid points, right, and that may be very expensive, correct. So, in this case my individual subtasks are not very good, they are going to incur too much of overhead. Okay. Now, what else can we do? So, if you look at this, you can also see that if I take all the elements in a diagonal, right, is there any dependency between them? No, right, because all of these elements do, let us look at the diagonal elements over here, right, they do not have any dependency among themselves and they can be run in parallel. In fact, all these elements can be run in parallel as soon as you have finished this diagonal element. As soon as you have finished this diagonal element, this can start. So, if I say, right, my tasks are the elements or grid points within a diagonal, okay, then I do synchronization only across these diagonals. Then for each one of those parallel tasks, set of parallel tasks, I do one synchronization, which is basically ensure that this is complete. Okay. I can possibly do that using some kind of a barrier, let us say, right. After that, I can actually initiate this set of parallel tasks, and when this set of parallel tasks is over, which I can ensure by means of a barrier, I can initiate this set of parallel tasks. That is one way of doing it, right. But then the problem here is that each diagonal has a different number of parallel tasks, right. Some parallel tasks are too small, some parallel tasks are reasonably big, right. So, you will have this parallelism which is not quote unquote balanced, and therefore, you will lose certain efficiency in this particular example. Okay. I do not have a solution for that, but I will try to use some knowledge from the application and try to solve the problem in a slightly different way. Okay. Now, the same example in place update, I have marked them as red and green, but in the text it is said as red and black. So, you read it whichever way you want. Okay. So, now what happens is that you can see that each green point, right, or black point if you want to call it that way, depends on other red points, but not on any black point, not directly on any black point. Similarly, each red point depends on black points and not on any red point. Okay. And for a moment, if I assume that okay, I do the computation of all the red points in one iteration and then all the black points in the next iteration, right. Then what happens is that all the red points can be done in parallel and all the black points can be done in parallel. Of course, I am violating some semantics of the original sequential program. In the original sequential program, this black point is supposed to take the new values of these two red points. I have not taken that, okay. But I know in this application, right, this will not affect my convergence condition. It may take a little longer to converge, but it will eventually converge, and I will probably converge to the same value, okay, nearly the same value within the error margin, right. Who asked that question? What benefit are you getting? Answer me. We are not doing unnecessary work. We are well, we are possibly doing some extra work, okay, because we may take more iterations to converge, okay. But what is the benefit that we are getting? You are now making all the red points parallel, all the black points parallel. We are not going to take. I am saying that we are not going to take. If you are not going to take. So, that is what I said. We are not going to obey that dependency between those red points and black points. We will compute all the black points, we will compute all the red points. In the next iteration, we will use this value. So, it is eventually going to propagate. So, the convergence will indeed happen. Okay. It may take a few extra iterations to happen, but now I have the advantage of being able to execute n squared by 2 parallel tasks, parallel subtasks. I may not want n squared by 2 parallel subtasks, because n may be very large, n may be 1024 or 16,000 something. Okay. I may not want that many, but at least I now have all my tasks to be parallel, and I can group them any which way I want, and I can exploit all my processors. That is the advantage I am getting. I am trying to parallelize this, but here we are making use of some application domain knowledge. In general, you are not supposed to do this. In general, unless it ensures that you are computing the same thing, you cannot violate those dependencies, right. That is important. You cannot violate those dependencies, because if it computes something else, you are not interested in that, right. But in this particular case, we know that it is only the convergence criteria which is getting altered, and eventually the convergence will happen. There is a proof for that. Therefore, you can make use of it, right. That is the point here. Okay. Now, okay, this is the entire code. I am not going to go through all of this. I am going to talk about certain parts which are interesting, right. In this particular case, let us see what am I doing. Okay. So, here I am parallelizing it for all the red points here, okay. And so, this both for all is basically for both I and j, but I am stepping in steps of 2, which means that either I am doing red or I am doing black. Okay. So, I am doing all of the red points in parallel, Similarly, I will have a loop where I will do all of the black points in parallel or the red points in parallel, whichever one you have done, correct. So, I can do that, okay, and then of course, I can somehow compute this diff, which is what I wanted to compute, and I will see whether the convergence is happening. Okay. Still we have to do a lot more things. So, let us just step through this. Okay. Okay. So, before you start the computation of your red points in this particular example, right, you have to ensure that all of these n squared by 2 parallel subtasks are complete. So, you have to somehow do that synchronization, because if you do not do, then you may be violating more dependencies, which may not be very beneficial. So, somehow you have to put some synchronization here, which would ensure that these n squared by 4 actually n squared by 4 parallel subtasks, okay, are all complete before you start the next n squared by 4 parallel subtasks. That is really what is needed, right, n squared by 2, not 4, sorry, n squared by 2. Okay. So, that there is some synchronization which is required, which you need to identify. Okay. But again, what I said here is that this n squared by 2 parallel tasks is again too fine grained, okay, and you may require too much of coordination overheads on that. So, we may want to group these tasks, some of these subtasks into a larger task, which is what we are going to call as a process. Okay. And I will show you how we can do that. We can do that using various types of assignments, one called block assignments, where you will consider contiguous sets of points, okay, contiguous rows or contiguous columns as a block. Okay. Or you can go cyclic, which may say that the 0th row, the pth row, the 2pth row and so on to be a task. Or you can actually have a combination of this, which is what is called block cyclic, that is also possible. Okay. Let us see. So, here is an example where I have divided this in terms of groups of rows, and each of these tasks together. I have not taken the red black example, but I have taken all the grid points in the n squared in this particular case as one block. Okay. So, this could be all of these subtasks could be combined together and then could be called as a task. Similarly, the next set of 3 rows, the next set of 3 rows and so on. I could have done this column wise, okay. Both of this are block. Okay. Here is an example of cyclic, where all the blue rows go to process 0, all the green rows go to process 1, all the red rows go to process 2 and so on. That is another way of doing this. Yes. There is some forking that has to happen. When we talk about specifically OpenMP program, we will tell you how exactly that is going to happen. When we talk about MPI program, what is the underlying thing there, I will talk about it, right. For now, we are trying to understand these parallelization steps and how do we go about getting them. That is really what we are getting into, right. Okay. So, maybe we need to stop somewhere over here. With this slide, probably we can stop, right. 5:45, Biswa is around, no? Okay. We are supposed to stop by 5:45, maybe we will stop by 6, right. So, the last step, which is the third step, which is involved in this parallelization, is about orchestration, and orchestration specifically puts how the interaction between these processes take place, and the way in which they interact would depend on whether you are following a shared memory programming model or a distributed memory programming model. If you are following a shared memory programming model, you will assume that the address space is shared and they can actually access it. You only need to ensure that proper synchronization is done, so that the appropriate values are accessed. If you are doing message passing kind of a thing or a distributed memory programming, then you have to ensure that the computations that you have done, appropriate data is sent to whomever who wants to receive that, and that particular process is doing the corresponding receive. And if you have multiple tasks and you want to synchronize somewhere that all of these tasks must be completed, then you will put an appropriate barrier for that, whether it is a shared memory programming model or a distributed memory programming model. So, you will introduce all of that, and that is essentially the step which is involved in orchestration. Okay. So, as I mentioned, in the case of a shared address space, you are going to use the shared address space and you will make sure that the interaction happens through the shared address space, but you will have to do appropriate synchronization, either using barriers or using locks. In the case of distributed memory programming, there is no shared address space. So, data has to be communicated by means of send receive messages, but you will also use barriers for synchronization. That is essentially what you will do. Okay. Now, we are going to look at the same okay, maybe we should take this up tomorrow and talk about this and parallel programming to certain extent tomorrow. So, maybe this is a place to stop. If you have any questions, we can quickly answer that, otherwise there is supposed to be a break and then we are supposed to resume at 6:15 or something like that, right. Any questions? Okay. So, let us stop here. Thank you very much.